The last state assignment strategy that we're going to look at is the one that is called one hot. So in this case, one hot means that we use one state variable for each of the states. That means that for all the state transitions that we have, two variables will always be changed. And if we go back to the same state, of course, no state variable will change. This aligns quite well with our overall strategy that we want as few state variables as possible to change when we do a state transition. So for gray and reduced dependency, we try to have only one state variable changing as much as possible. And in this case, we will make sure that we always have two. We will not have one, which heuristically perhaps would be the best case, but we will also make sure that we will never have more than two. So this is kind of a nice compromise in the way how many state variables are changing when we're doing a state transition. So let us return to our detector problem and do our state assignment. And we will use this one hot strategy to do our state assignment. We have our state transition table here. So the first thing that we want to do is just to assign the states. So we use that Q1 will represent state S0, and we indicate this by having state S0 as 1, 0, 0, 0. S1 will similarly be represented by Q2, so this will be 0, 1, 0, 0. Then for S2 we will have 0, 0, 1, 0, and for S3 we will have 0, 0, 0, 1. So from this, let us fill in the state transition. So if we start with state S0 with a 0 input, we see that we go to state S1 with a 0 as an output. So we will go to the state that we have denoted 0, 1, 0, 0, and we will have a 0 as an output. Then if we have a 1 as an input, we will stay in state S0, so this will be represented as 1, 0, 0, 0, and the output will be 0. So for the state S1, if we have a 0 as an input, we go to state S2, which we have represented as 0, 0, 1, 0, and the output will be 0. And with the input 1, we go to the state S0, so we go to 1, 0, 0, 0, and we output a 0. If we are in state S2 and we have a 0 as an input, we stay in state S2. So here we represent this as 0, 0, 1, 0 with output 0. And with a 1 as an input, we go to state S3. So here we go to state 0, 0, 0, 1 with a 0 as an output. And if we are in state S3 with a 0 as an input, we go to state S1. So this will represent it as 0, 1, 0, 0, and the output here will be 0. And finally, if we have a 1 as an input, we go to state S0, which we denoted 1, 0, 0, 0, and the output here will be a 1. And now we want to do our Kernel Maps, and when we do the Kernel Maps, we will see one of the drawbacks with this one hot state assignment, because what we have now is that we have as many state variables as we have states, because we use one state variable to indicate each of the states. And then we also have our input. So in this case, we will have 5 variables in our Kernel Maps. So looking at the Kernel Maps for Q1 plus that we have in this and this map here, we will divide this into 2 maps because we can only have 2 variables in each dimension. So for the first map, this will represent the map when x equals 0, and the second one will represent the map when x equals 1. And for both of the maps, we have the state variables, so we have Q1, Q2 for the rows, and we have Q3 and Q4 for the columns. But if having larger Karnaugh maps was the drawback, the benefit of the one hot state assignment strategy is that we will have a lot of don't care terms in our Karnaugh maps. And with many don't care terms, it means that we can have very large rectangular blocks and very large prime implicants that we make in our Karnaugh maps. So we can see the size of the tables and the number of don't care terms as a trade-off that we have here. The prime implicants have already been indicated in our Kernel Maps here, but we see, for example, that for each of them we only have one and a very large prime implicant. So each of our next state functions can be described using only one implicant that we have. And the reason for this is that we have so many don't care terms and very few ones. So when we want to cover our ones, we use as many don't care terms as we need in order to make as large rectangular blocks as possible for each of the ones. And writing our functions here, we can see that q1 plus can be written as x q3 prime, because we have the prime implicants in the table where x equals 1. q2 plus can be written as x prime, q2 prime, and q3 prime. q3 plus can be written as x prime, q1 prime, and q4 prime. And q4 plus can be written as x q3. And we also have our output function that we call u here, and this we didn't make a Karnaugh map for, but what you can see here is that this function only has one in our Karnaugh map, and this one we will have when we are in the state S3 and when we have the input value 1. So looking at S3, it means that we are in the state where we have only Q4, which is a 1, and then the X input must be a 1. So we can actually write this prime implicant immediately by just looking at the straight state transition table. And if we look at the number of implicants that we have here, so in total we have only one implicant for each of the functions. None of the implicants are the same, so if we want to realize this, we need to use 5 implicants. And we can take the exact same approach for our modulo 6 counter when we want to do the one hot state assignment. We start off with our state transition table, then for each of the states, and in this case we have 6 different states, we use one state variable to indicate the state. So we put a 1 for Q1, Q2, Q3, Q4, Q5 and Q6 respectively for each of the states S0 to S5. And then we will have a 0 for all the other state variables. And for the input X here, if we have a 0, we can just write down the state transition table in this way as we did before. Unfortunately, now it is not possible for us to use Kernel Maps because we have 7 variables. So we have Q1 to Q6 and we also have the input variable X. And it is not possible to use Kernel Maps for 7 variables. Instead, we have to be a little bit clever here. So let us see if we can understand what the function Q1 plus should look like. Well, Q1 plus is the first bit here when we have our state transition. So Q1 plus, we see that Q1 plus is a 1 in this case here, which means that it is a 1 when we have Q4, because it is this one that we have here, and when we also have X as a 0, so we can write this as X prime. It will also be a 1 here in this case, so it will be a 1 when we have Q3 and when we have X, the input, as a 1. So we can write this as Q3X. And we can do the same thing for the function for Q2 plus, where we can see that this is a 1 here, which is when we have Q5 and we have an X prime, and it is also a 1 here, which is when we have Q4 and X. So similarly for Q3 plus, this we can find here. So this will be when we have Q6 to be a 1 and we have X prime, And we can also find it here, that is when we have q5 and x. And for q4 plus, we find a 1 here, so this will be when we have q1 x prime, and we will also find it here, so this will be when we have q6 x. And for q5 plus, we do the same thing, so we have a 1 here, so this will be when we have q2 x prime, and we also have a 1 here, which is when we have q1 x. And our last function, q6 plus, it will be the 1 here, so it will be when we have q3 x prime, or the one that we find here, which is when we have q2 x. And here we do not have an explicit output function, so these are the functions that we need to realize. So if we look at the number of implicants that we have 2 implicants for each of the functions. None of the implicants are the same, so we will have in total 12 implicants needed in order to realize this function. So even though each of the functions are very simple, we have quite many functions that will add up to our number of implicants.